So hello. I'm sorry for being late. It was, well, because of traffic anyway. So I'm going to finish what we started last time. So we're studying the model, which we call spontaneously stochastic Arnold scat. So the model is designed such that we mimic the multi-scale structure of the space and time, and so at each space and each time, our variable is taken on a torus. So it has two phases, which is two coordinates modulo 1. Okay, and scale n. So scale correspond to n, and n is integer, so it's 2 minus n. So n is integer starting from 0, and times are given in terms of the turnover times, which are the same as scales. So times can be m tau n, where m is also integer. So at the end, we end up with a structure, which I put it here. So we have timeline, and we have scale, which will go down, so smaller and smaller scale. So the n is 0, then 1, 2, 3, 4, and so on. And so at 0 scale, the turnover time is 1. So it's 1. 2, and at each next scale, the turnover time is twice smaller. So we divide every time this piece by 2, then the next by 2, and so on. So this is our and so on. So this is our space-time. Okay, so and in each node we have the variable unt. So what we learned, so there are so we study the initial value problem. Initial values are given at time 0. So these are initial values. And then we need to define the values at positive times, and this is given through the interaction. So first of all, there is an evolution at each scale, its own evolution, and it respects its own turnover time. So it's the same evolution within turnover time. So evolution here is the same as here, is the same as here, and so on. And then we have an interaction in a way that the smaller scale influences the larger scale. So the smaller scale, imagine two vortices, the smaller vortex somehow within a large turnover time makes some influence to the larger one. So we draw this diagonal arrow. There can be other diagonal arrows, but we just consider this one. Our goal is to make something simple which we can solve. So each rectangular is just the same. And then we need to make sense of the arrows. So what we do is, so first we take initial condition. So it's given un at time 0. And then we take equations of motions. equation of motion is what is given by an arrow, and each arrow is Arnold-Ket map, so it's A. So if you want to define what is at the next step, is given by the Arnold map from the previous step, and my Arnold map from the previous time, but at smaller scale. So these two values give the value here. So UN at next time. So at the next time means plus 10 over time at that scale. So if we want to start here, so we go to this point, and this is tau 1 in this case, right? It's 1/2. Here it will be 1/4, 1/8, and so on. So in one turn over time, so this smaller vortices, they make turnover at smaller times. So this turnover time, value here is taken from this one and from this one, with additional action of the Arnold-Ket map. So Arnold-Ket map is a map which maps x, y to, I don't remember what it was, 2x plus y, x plus y, right? X plus y. And it's on a torus, so it's all modulo 1. Okay. So I recall you the two results which were obtained. The first result was about non-uniqueness of the initial value problem. So what we found is that, so first immediate consequence that since you have all the conditions on this line, so immediately the next, in one turn over time, we know everything, because this is exactly our formula. So at these points, which we put green, these are well defined, uniquely defined by initial conditions. And then we've also proved that an interesting thing, that the other points are actually not at all uniquely defined. And what you can do, you can put red points everywhere on the first line. It's not red. And then what we do, and then we put red points at each even position. So it's at each even position. It's here, 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 here. And so on. So we proved the theorem that telling that you can assign any value to the red point, and whenever you assign any value to the red point, the rest, which I don't remember which color it was, that's a nice color. So the rest will be uniquely defined. So whenever you assign values to the initial condition and to the red points, the rest is unique. So that means that essentially there is a huge freedom of giving solution to the initial value problem. So the fact that we have equation of motion which gives you the next point in terms of the previous doesn't give any clear answer to what is the solution. So it's not enough to give initial condition, because you see, even though that each next point is defined in terms of previous, it cannot be defined in terms of zero-time values. And there is huge freedom in the sense that half of the values you can just assign arbitrarily, the rest will be defined. So this was one message which is quite, I would say, counterintuitive, and it has to do with the fact that if you take one node and see what is influencing this node, so which which of the previous values make an influence, you will see that you not along the all, you along some of the lines you really come to the initial to t equals 0, so you're influenced by initial conditions, but some of them just go to minus infinity directly. So the situation when you have formally deterministic equations, but multi-scale system which has a scaling both in space and time, it allows to bring information from infinity, from infinitely small scale directly to arbitrarily large scale, infinite time. So there is something comes from infinity, and this is how the regularization come into play, and we introduced regularization. So we introduced a regularized system. So a regularized system was introduced by telling that all u and t are identically 0 for n bigger than certain n capital. So a regularized system, which you can say n capital regularization. So n capital gives you the scale at which you regularize. So it's like viscosity. So it's like a Kolmogorov scale in a turbulence. So we say that n capital is our Kolmogorov scale. So everything at smaller scale is suppressed by viscosity. In our case, the suppression is extreme. So we just put 0. So in other words, so what we do? What we do, we put 0 here. So everything below is 0. So in this case, whenever you want to compute anything at each point, you follow different trajectories, and you either hit the initial condition line, then you know what is the value, or you hit the n capital plus 1 line where it's 0. So it's clearly that it's now solution is uniquely defined, because everything is 0. Nothing comes from infinity. From infinity comes 0, what comes is 0. So we have a unique solution. Depending on regularization, of course. And this dependence can be still very strong. So the second theorem, what we proved last time, is that considering initial condition, so we take just initial condition for which are convenient to construct the proof. So consider initial condition where everything is the same. So for almost every A, so this is, remember what means almost every. It means that some A may not satisfy our condition, but this will be zero measure set of A's. So, but for almost every A that you can choose, the limit there exist infinitely many solutions obtained in the subsequence limit u n of t equal limit I goes to infinity u n I t. So here we have a subsequence, and 1, and 2, and 3, going to infinity, right? So what it tells us is are two things. The first thing is that for almost every initial condition of this form, we don't have a limit of the solution when n goes to infinity. So what we want to do, we put regularization at certain capital N, and the natural thing would move this scale to infinity. So it's just like we do with viscosity. So the scale at which viscosity x becomes smaller, smaller, and smaller. So, and we may expect that there will be some limit of this process. So we get a solution which will be solution of our original problem, but obtained from somehow physically like condition of that we regularized, but then removed the regularization limit. So third theorem tells that it almost never happens. So the limit does not exist. At the same time, though limit does not exist in a normal sense, limit may exist in a subsequent sense. So we don't just send n capital to infinity, but we send it to infinity along certain specially chosen subsequence. And this is okay. So the theorem tells that we can choose subsequences which converge everywhere. So really, we can carefully choose where to cut such that it will converge everywhere. But this is non-unique. So still we have very strong non-uniqueness, because this way different subsequences will lead to different solutions, and there are infinitely many of them. So maybe there is improvement because infinitely many, but maybe less infinitely many, but still infinitely many. So situation is very bad. So what we would do in this situation is the following. So now what we do is that we introduce stochastically regularized system. So what we do is, okay, we still put everything 0 here, but then we add noise. So it's quite natural that there is, at small scale, there is always noise, like molecular noise or uncertainty or whatever noise you want. We know that whenever we go to a very, very small scale, it's not any more deterministic, because fluid dynamics is macroscopic form of the molecular motion. So at very small scales, there is a noise which is absolutely natural. So there is noise here. And we will add noise, but we will add it. So again, we don't need to be very natural. So we add noise in the simplest way. So what we do, in principle, we can add noise here everywhere. But what we do, we just put it here, just one point. So here we add a random number, exactly at the place where we cut. So what we do, we first use this condition. So it's still 0 for n bigger than n, and we take the initial value at the cutoff scale as the value which is given plus random number. Random number. So what is important is that it's a random number with absolutely continuous measure. probability measure. It just means that it's a random number, but it's somewhat distributed. So for example, C is uniformly distributed in some interval between 0 and epsilon. And we will see that epsilon doesn't matter. So we give a number which is whatever you want. For example, it's distributed between 0 and epsilon. So some small uncertainty. And we will see that apart from this condition, nothing is important. So it's okay. So what's now? So now, initial condition is random. So now what we have is that we have a deterministic system, deterministically evolving system with a random initial condition because we put a random number here. So initial condition become so what is initial condition is u n at time 0 for the solution n. It's u n 0 for n bigger than n, and u n 0 plus xi for n equal n. So we make a small kick here. And xi is a random variable, so the xi has a probability density rho. We just define the probability for getting different values of xi. So everything what we need is continuous, absolutely continuous, means that there is this function which is measurable. Okay. So essentially what means that it means that initial condition u0, 0, u1, 0, and so on, until n for the regularized problem. We just call it briefly zeta 1, zeta 0, zeta 1, and so on, zeta n, is a random number, is a random vector. In where? So each one is in a torus, and there are n plus 1 of them. So it's in the torus 2n plus 1. And of course, we can write probability density. With probability density, so how you write probability density? First are deterministic, so it's the delta functions. So the probability density, so probability, let's say directly the density probability measure. So it's already not a density. Probability measure, initial probability measure, mu ini for the n regularized problem. So what it is for first n variables is deterministic. So it's of just delta functions. There is a misprint here. Good. So this is just a product of the delta functions, which gives a measure which is concentrated on fixed values. And then we have a distributed value because this is a random number. And how you do, you have to take this density but shift it to this value. So this gives you rho zeta n minus u 0 d zeta n. So that's initial condition now. So formal initial condition for our problem is this. It's a measure. So we put initial condition as a measure, which is exactly the deterministic initial values except for the random kick here. And when n goes to infinity, it goes to it disappears. So now, since solution of regularized problem of deterministically regularized problem is unique, we have a map that maps initial condition to the n-regularized solution. So for each initial condition, we have a solution. And the same map can be applied to measures, right? So whenever you have map which maps point to a point, and it is a good map, like measurable, then you can also apply it to measure. So if instead of initial condition, you have initial measure. So the initial measure it will be mapped to the measure which is a measure on the space of solutions. Right? So if for every initial condition we have a solution, so for giving a measure on the initial condition, we give a measure on solutions. And we know where this measure lives because we know that all the solutions, given initial conditions, we know all the solutions. Given initial conditions, well, for each given initial condition, we have a finite dimensional space of solutions. So there is it's a well-defined construction. So the definition is that the initial value problem with deterministic initial condition is spontaneously stochastic if exists a non-trivial limit measure in the limit so mu, so which limit? Limit of n goes to infinity, mu n should give us a measure, not subsequence. So what we tell? So we have solutions. So what this construction gives? So we have a initial condition. For each initial condition, give us the solution. For initial condition given by this measure, so this measure is just our initial conditions, but with small uncertainty. It gives us the measure of the solutions. So now we want that this measure, when we regularize lower, 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 and lower, converges to some other measure, which is not something trivial. It's not just a point. And it converges normally. Just n goes to infinity, with not in a subsequence as before, just a unique limit. And if this limit exists, so why it is spontaneous solution? Because if this limit exists, what you can directly see is that this measure will satisfy initial condition. So at these points, it will be deterministic, right? Because all these measures are deterministic at every point. So this measure will give a measure of the on a space of solutions which satisfy exactly initial conditions. And since n goes to infinity, it satisfies exactly all equations at every point. So this is will be measure on this space of non-unique solutions that we proved in theorem 1. So in theorem 1, we showed that given initial condition, there is infinitely many solutions. So this will be measure exactly on this space of on this space of non-unique initial conditions. So the theorem that I'm unfortunately not going to prove, but this is rather new result. So whoever wants to see the details, so details actually are the following. So details has to do with Arnold-Cat map. Arnold-Cat map, what it does, it stretches in one direction, compresses in another. And what it does, since it's on a torus, it starts to stretch any arrow which is distributed, maybe even in a small region. It stretches the region and starts to roll up its on a torus until this arrow, even if it's concentrated in a small interval, it will completely fill the torus. So as we go up and up, it starts to increase and increase this arrow. And as we take the limit of n goes to minus infinity, this process becomes stronger and stronger and stronger until the very interesting thing happens. So the theorem that the proof you can see in the paper in arXiv. So the proof is actually not very so complicated. I think it can be followed by many. So it's arXiv paper by myself and Artem Reibekas. And it's arXiv 2.1.1.1.0.3.6.6.6. So you can take it from my webpage, for example. So the name is Spontaneous Stochastic Arnold-Cat. So the theorem tells the following, that for any initial condition and any xi, so any arrow which is random number with the density. So it's not absolutely continuous probability measure. So any xc, the stochastically regularized, so the initial value problem is spontaneously stochastic. And mu, so the measure that we obtain is uniform on a space of all, remembering that non-unique, right, solutions. So what we have? So what we have is that whenever you put an arrow just at one place here and take a limit, it turns out that you get statistically very nice convergence as n goes to infinity. And this convergence leads to the results which does not depend on xc. It doesn't matter what in an arrow you put. The statistics will be the same, and it will be uniform measure on all non-unique solutions, which means that all non-unique solutions can be chosen with exactly equal probability. So the measure that you get in the limit, the probability measure, does not prioritize any of the solutions. So you had, so we said that there is infinitely many solutions. These red points can be taken arbitrarily. So all of these solutions are just equally probable when you take regularization, send it to 0, but take into account that there is an arrow. Doesn't matter which one. So there is this duality which tells you that, in fact, non-uniqueness here is not just intrinsic, but it's very intrinsic in a stochastic way. So the system will choose non-unique solutions randomly, and whenever n is very large, so whenever viscosity is very small in a sense, so n is very large, you cannot predict which one of them, because arbitrary arrow that you put here, there, arbitrary noise, will just give you a random realization. And this will be a random realization which satisfies fully deterministic initial value problem. So that's a paradox. And for this system, it can be proved. So I really invite you to read the article. But I think that I probably will not give the proof. So it's relatively technical, but not too large. So if you're interested really in the details how you do this. So essentially how you do that is because since the system is linear and simple, for every point you can find explicit solution for the problem. So just explicitly express this value in terms of initial condition and noise, and then take a limit and prove that the measure will converge in a certain sense. In a weak sense, it will converge to the measure which is uniform on space of all solutions. So I think that that's it. Of course, I'm not giving a message. I don't want to give a message that whenever you have non-uniqueness, all solutions are equally probable. It's just specific example when they are equally probable. But the message is that in this multi-scale system, you can typically, and then with the non-uniqueness, one of the typical scenario is that the choice will be random with some probability distribution over the non-unique solution. So this probability distribution will be defined by the way how the system interacts, and not by the way how you put a noise. So noise, it's important that some noise is introduced in the process and removed, but what noise doesn't matter. What is important is the system itself. So it will amplify the noise in a way that it likes, and will make a certain choice between solutions which satisfies the deterministic initial values condition and deterministic equations. Yeah, so that's it. That's it. So let's make interval. Eu tenho que sair, mas eu vou ver no YouTube. Combinado, não? Porque eu tenho que ir para buscar Yuri na escola e é longe. Então eu vou ver no YouTube. Que eu também quero saber. Mas sem perguntas.
Hello. Okay, so I am Silvio Campolino. I am a PhD student here at IMPA, and I'm going to give this half of the lecture for Alexei. And I'm going to talk about dissipative Euler flows. So it's essentially a summary of some mathematical results, recent mathematical results, towards the solution of this so-called Anaxagoras conjecture. Okay, so let's give an introduction, introducing the two models we have in this course, right? So it's essentially the Navier-Stokes equations and the Euler equations. And the difference between them is just because we have this viscosity term here in the Navier-Stokes equations. So this is a dissipative term. And the object of the course is turbulence. And so we believe that somehow developed turbulence is modeled by the Euler equations as we send viscosity to 0, or equivalently when we send Reynolds to infinity, right? But of course, in what sense? And this is the core of the course. Because we have the equations, we have the Navier-Stokes equations for finite viscosity. We have the Euler equations with no viscosity at all. But what is the meaning of the solutions, right? And this is the object of the course, to make sense, give sense to the solutions to these equations in such a way that it represents the phenomenon, the turbulence phenomenon. Okay. And Alexei and Simon, they talked a lot about this topic, and I'm going to talk about a specific object today, which is the energy and the conservation of energy. So about energy. So energy, we know from the first lectures by Alexei that the total energy of the flow is given by half of the integral of u squared. And if we want to study the time evolution of the energy, we may derivate by time and substitute the equations, the Navier-Stokes equations or the Euler equations, and obtain, after several manipulations, we obtain a balance for the energy. So if we start from the Navier-Stokes equations, we obtain this energy balance. So the variation of energy is equal to minus the viscosity times the entropy, or 2 times the entropy, which is the integral of square of the vorticity. And of course, this term comes from the dissipative term. So if viscosity is 0, as in the Euler equations, we have energy conservation. So energy is conserved exactly because there is no dissipation mechanism in the equation. But let us recall that these relations, they hold for classical smooth solutions. And this, of course, this holds for classical solutions exactly because in the deductions we use a lot of things about differentiability, like integration by parts. We assume differentiability and all properties like that. So in some sense, we are always talking about smooth solutions when we talk about energy conservation in the Euler equations. A natural question is, does energy dissipation vanish in the inviscid limit? So if we want to model turbulence from the Euler equations, and the Euler equations are conservative, this term goes to 0 when we send viscosity to 0. So this is a very natural question from a mathematician, and the answer is no. And the answer comes from experiments, from physics. So this is the so-called zeroth law of turbulence, or the energy dissipation law, which states that energy dissipation converges to a finite positive value as viscosity goes to 0. So here we have a graph. Here we have Reynolds number, and here we have dissipation. And these points are several simulations. So when we consider the dissipation along Reynolds number, as Reynolds number goes to infinity, we can see that the dissipation converges to a finite positive value. So it does not go to 0. And this law is confirmed from lab experiments and numerical simulations. In this case, they are numerical simulations. So the message here is that turbulent flows are dissipative. So on one hand, turbulent flows are dissipative. But on the other hand, smooth Euler solutions are conservative. And there is no paradox here, actually, because we just addressed the conclusion that we cannot model turbulent flows by smooth solutions. Actually, experience shows that turbulent flows lack regularity. And during Alexei's course and Simon's lectures, we saw several signatures of this lack of regularity. So we saw the possible blow-up in the Euler equations, which is essentially a loss of regularity. We saw in Simon's lectures the enlargement of inertial range, which means the development of small-scale structures, and so on. So therefore, the message is that we should not work with smooth solutions. We should focus only on solutions with low regularity. Okay. But how to make sense of low regularity solutions to the Euler equations? So if we take a look into the Euler equations, we realize that we need regularity because there are derivatives like time derivative, spatial derivatives, derivatives of pressure. So how to make sense to a solution which has low regularity? And the answer was given by Alexei in his lecture about the Berg's equation, because we can work with weak derivatives, weak solutions. And the idea here is the same. So we take the equation, we multiply the equation by a smooth vector field, phi, which has compact support, and we integrate both by time and space. So this is what we obtain. So we have all terms of the equation. We have the time derivative, we have the nonlinear term, the pressure, everything multiplied by phi, right? Now, if you assume that the solutions are smooth, then we can integrate by parts. And so essentially, we are passing all derivatives to the test function. So we pass the time derivative to the test function. Here we pass this is just a matter of notation, but we are passing this nabla to the function phi. And we pass the gradient of pressure as a divergence to phi, right? And now we have, after this procedure, we have two different, let's say, two different equations. We can do the same for incompressibility to demand the vector field to be incompressible as well in a weak sense. And then we arrive at these two formulations. The first one is called a classical formulation. So it's a field satisfying this formulation is a classical solution. And it should be differentiable. This is why it is in a classical sense. So it demands differentiability. But in the second equation, we can see that all derivatives are in the test function, which is smooth. But there are no derivatives in the fields. So this expression makes sense for functions which are way less regular. So they can be, for example, not even continuous. It can be, for example, L infinity, measurable functions. So this is the formulation we have for to give sense to low regularity solutions of the Euler equations. They are called weak solutions. And from now on, we are going to talk only about weak solutions. Okay. Okay, so going back to the theme of energy conservation. What is the degree of regularity we require to the flows for them to be conservative? So we saw that smooth solutions are conservative, but what is the degree of differentiability we need? And this was answered by Onsager. Not answered, but actually conjectured in 1949 in this paper. There are some notes about statistical hydrodynamics. And Lars Onsager, he performed the following conjecture. It's composed by two parts. The first part states that solutions to Euler obeying an alpha Hilder condition for some alpha greater than 1/3 must conserve energy. So it's a regularity condition, right? Just remember what is a Hilder condition. Separation of fields, the difference of fields separated by a scale L should be bounded by up to a multiplicative constant by L power alpha. So this is a Hilder condition. When alpha, if we put alpha equals to 1 here, we have Lipschitz condition. And for alpha less than 1, we usually call it fractional. It is a Hilder condition. Okay, so if alpha is greater than 1/3, then it conserves energy. Of course, every differentiable function is Hilder condition. It's Hilder in this order. So differentiable functions, C1 functions, they are conservative, as we saw, but it can be way less regular. It can be only C alpha with alpha greater than 1/3. Okay, the second part of the conjecture concerns dissipation of energy. So for every alpha less than 1/3, there are solutions to the Euler equations obeying an alpha Hilder condition which dissipate energy. So this is a conjecture, and it's the part that states that somehow when they are less regular, they will not conserve energy anymore. Okay. And at that time, this was a conjecture, but now, today, it's a theorem. So I will follow a review of results, recent results on the last decades, proving these two statements. Just a remark, of course, two remarks actually. Of course, let us remember that 1/3 is a very special number for turbulence. Simon, in his lecture about Kolmogorov's theory, he showed that 1/3 is actually the exponent separating scales when we have a constant flux solution, right? So it's predicted by Kolmogorov as a very specific exponent for the velocity field when we have a turbulent solution. So there is a link between mathematics and physics in this sense, right? And a second remark is that, of course, here we should include 1/3, since 1/3 is exactly what we expect from physics. The 1/3, the alpha equals 1/3, we also include in the dissipative term, right? So 1/3 is also dissipative. Okay. Okay, so the first part of the conjecture was completely proved in 1994. The first paper released was this one by Gregory Inc. in 1994. He exploits Fourier analysis and the idea of cascades of energy to make a proof. And mathematicians claim that it's not a rigorous proof. It's just a partial proof because it's not stating all possible spaces and functional spaces where they are defined. It's not rigorous, so they claim it's a partial proof. But a complete rigorous proof came only months later by Konstantin, Weimann, and Tipi, also in 94. And it's a complete proof, and it's established in, they are just some estimates in Bezov spaces. So they perform all definitions of the spaces and perform some estimates and prove that if we have that threshold of alpha 1/3, then they are conservative. So this part of the conjecture was proved, let us say, pretty fast. At least the two steps here are separated only by months, even though 94 is separated a lot from the 49 paper by Onsager. The second part of the conjecture was completely solved 4 years ago, so 2018, only in 2018. But differently from the first part, it took almost 3 decades of steps towards the solution. So here, this is the timeline towards the C1/3 regularity. And we can see that it starts from 1993, and it finished in 2018, 19. And the proofs, they are essentially establishing, constructing by hand solutions of the Euler equations, which are dissipative, or they are non-conservative. But they perform this because of technical issues. They perform this in different spaces, and we can see that they are somehow, in some sense, increasing regularity. So we start with very low regularity, which is less constrained, so we have more liberty to deal with the solutions. So it starts with L2 in space and time, and then we go to L infinity, then we go to continuous functions, then we achieve Hilbert continuous functions, and we go increasing the exponent until the 1/3 threshold. Okay, and we can see also a separation in time between the first papers and the last ones. And this separation is actually because in 2009, this is the groundbreak paper, which established the technique of, used the technique of convex integration in hydrodynamics. And because of that, we have a very fast development after that, because all of them use this technique. Okay. So now I will reveal some of these papers in a row to see what is the construction, the results, and everything. Okay. So this is the first paper. Is by Scheffer in 1903. Okay. It's a construction of a solution in L2, and it's performed on a 2-dimensional space. Okay. And the solution has compact support in space-time. So this is the theorem of the paper. There exists a non-zero weak solution to the Euler equations in the plane, so 2-dimensional space, such that this solution has compact support in space-time. So this is very counterintuitive because we can visualize that we have a zero initial condition, so nothing in space, nothing in time. And as time evolves, something occurs because the solution has compact support, and then after some amount of time, it remains smooth, steady zero again. Okay, so this is a very counterintuitive example, and it's a very, very nice theorem. So a few comments about this theorem. Of course, I will not give proofs of any of them. It's a very long paper, and it's a construction. So he constructs the solution by hand. And it's in a very complicated fashion, and the solution is extremely discontinuous and unbounded. So velocity is somehow growing to infinity in some points.
So this notion of a weak solution is just a distribution solution, right?
Yes, exactly.
There's no other condition on top of it, right? Just
No, they are just distributional solutions, yes. Just a remark about your question. There are several ways in defining a solution for a given equation, a weak solution. And for example, for the Euler equations, you can define a weak solution demanding in that integrate by parts technique. You know, you can perform for the equation and the incompressibility, but some authors prefer to integrate only the equation, the momentum equation, and require the test function to be incompressible. Exactly. So there are several formulations, and actually one of the trends in research is exactly which one we should use, which one gives benefits in some techniques, you know, in PDE techniques. But they are essentially all the same here, and we can prove also that they are somehow different, but also most of them are equivalent. Okay. So the solution is extremely discontinuous and unbounded. So this is it's a nice result, but somehow it's not very physical because velocities go to infinity at some point, right?
wide solution, right?
Yeah, wide solutions. Yes, I'm going to talk about this name in some slides after. And another thing which is not nice is that the solution is constructed in L2 both in space and time. So it's not in energy space, which would be L2 in X and L infinity in T, right? So the energy may be exploding at some point, right? So it doesn't necessarily has finite energy. So it's again something which is not so physical, right? Okay. But a nice corollary is that, and it's a very important message, is that weak solutions are not unique. They are not unique. They are non-unique, because the zero solution is a trivial weak solution, right? So we have a zero solution is a trivial solution, and we have an additional weak solution, which is this one he constructed. So weak solutions for the Euler equations are non-unique. Okay. The proof of that paper was very, very complicated. And some years later, in '97, Schniegelmann performed essentially the same result, but with a different proof, which is a little bit more physically motivated. So it's in the same space, and it's in L2 Tx. Now, just to get rid of problems of compact subdomain of the solution, he works in the torus, so you don't need to talk about compact support in space. And the solution is compact support in time. So the theorem is essentially there exists a non-zero weak solution to the Euler equations in this class, and a certain constant C, such that U is equals 0 away from the interval minus t to t, right? So it's essentially the same thing. You have nothing going on until the time minus c, and something happens, and something non-trivial happens, and then everything becomes 0 again after some amount of time. And some comments about this paper. It's essentially the same result as given by Scheffer, but the construction is different. It's a little bit more simple, still very complicated. Less abstract because it's physically motivated. He introduced the notion of ghost forces. And I'm going to explain those ghost forces in the last part of the talk. But still, it's not in the energy space. It's not. It's still in L2 space, so it doesn't necessarily have finite energy, right? Okay, so these two papers, they introduce this notion of a solution which has compact support in time. And I just want to make an analogy. This is from the movie from Jurassic Park, because mathematicians like to give this analogy, because I don't know if you remember, it's a very famous movie. There is a scene where people are on the car in the middle of the rain, and we have some glasses of water in the car, and we can see that the water is somehow out of the blue it's trembling, right? It develops a movement. And apparently there is a sudden movement, but some minutes later we discovered that there is a giant dinosaur trembling the ground and provoking the trembling of the water. These so-called wide solutions are like that, except that there is no dinosaur. So this is the difference, because we have this sudden movement, but no external forces, because the dinosaur is the input of force. He's shaking the ground, right? And with the wide solutions, there are no external forces. There is no force on the right-hand side of the equation.
Sorry. So those solutions, they start in fact in a state of complete stasis, like U is zero everywhere, and somehow U is not zero anymore.
Exactly.
And wouldn't that be, instead of dissipation, like creation of energy somehow?
Exactly. It's strictly dissipated. We have some creation of energy, and then energy is depleted. Precisely. And this is actually something we are going to talk later, because this is somehow required by the conjecture. So they're still somehow away from answering the conjecture, not only because of the spaces and regularity, but also because of that. Okay, so this is exactly the scenario that Arthur just mentioned. The fluid is at rest initially, then something happens out of nothing, out of the blue. Then the fluid comes to rest again, and all of this with no external forces. Okay, this is the mathematics. Okay. So let us continue with the solutions. Then the papers. Then in 2009, we have this groundbreaking paper by Camilo Delelles and Laszlo Szekelyhidi. They construct a solution in L infinity, in both space and time, T and X. Now the solution is in any dimension of space, Rn, greater or equal than 2. So it's not restricted to the plane. And the solution has compact support in space-time. This is the theorem. So there exists a non-zero weak solution to the Euler equations, such that this solution has compact support in space-time in this class. Okay. Okay, so it's somehow very close to what we saw on the first papers, with some advantages. It holds for any dimension, any greater or equal than 2. The resulting velocity field now is bounded, which is interesting because it's in L infinity, so it's bounded, which is way more physical than the L2 condition. And the solution is in energy space because it's in L infinity with compact support in time. So we can integrate the square of this object. So it has finite energy, which are very nice physical conditions we demand from the solutions. So it's a very interesting that we have these additional conditions. But which is the more interesting thing is it was the first systematic use of convex integration in hydrodynamics. So it's somehow, you are not constructing something out of the blue by hand, and you are applying a systematic technique. And this systematic technique it comes from geometry. I'll talk later. But first used in hydrodynamics in this paper. And after this paper, we have a very fast development of the results using this technique. Okay. And this convex integration is somehow you just produce a sequence of approximations of your solution. And you, at each step, you are making a perturbation of the solution. And this perturbation you should construct by hand. So you need a gradient to construct this perturbation. And for this paper, they use planar waves localized in physical space. And this ingredient changes along the papers, and this is why they improve the regularity of the solutions. Okay. So the next paper is 2013 by the same authors, Camilo Delelis and Laszlo Székely. And now we are working with more regular solutions. They are continuous, both in time and space. It's a three-dimensional torus. And now we have another very counterintuitive result, very interesting, which is the following. Now, we are not just constructing by hand a solution which has compact support in space-time. Now, we prescribe the energy. We say, I want a flow with this energy profile, and they construct to you a continuous flow with this energy. So this is the theorem. Assume that E, from the interval 0, 1 to R, is a positive smooth function. Then there exists a continuous weak solution to the Euler equations, so in C0, whose energy is E of t. So this is a key ingredient if you want to, as Arthur just mentioned, if you want a strictly dissipative solution, because now we can prescribe an energy profile which is indeed dissipating, right? Of course, you can also prescribe something which is constant, something which is arising. You know, you can prescribe anything with these conditions. It's a strictly positive smooth function. Okay. And again, it uses convex integration, but with different ingredients. So at that step of making the perturbation of the solution, instead of using planar waves, we use Beltrami flows, which are they are stationary solutions of the Euler equations, well-known stationary solutions of the Euler equations, which are acting somehow in a very specific scales. So you can prescribe this perturbation at smaller and smaller scales using this Beltrami flow. It's a steady-state solution well-known from many years ago. So they use these as a building blocks of this convex integration procedure. Okay. So we can impose the energy, dynamical evolution, and this is surprising result provides a strong non-uniqueness because now we don't have only two solutions, right? The 0 and another one. Now we have, for any profile, we have a different solution, right? So there is a strong non-uniqueness. And now we are able to construct strictly dissipative solutions. And just a remark, this proof also holds for two-dimensional space. It was established by Chauffroux in 2012. It looks like it's earlier, but it's just because the preprint of this 2013 paper came before 2012. So it's just, and this was not published. It's just a preprint. Okay. Later, we have improvements of this last result. So it's essentially the same technique and the same building blocks, Beltrami flows, but with more machinery from PDE. And they can show that the same steps, they can prove that actually the procedure with slight differences, it converges in C alpha with alpha less than 1/10. And in this later paper, in 1 year later, they show that actually we can extend to 1/5. And here we have more guys working together. Besides Delelis and Székely, we have Philip Isett and Buchmaster. Okay. But essentially, it's the same technique, the same results, the same theorem, except for the regularity of the solution. Okay. And finally, we have, in 2018, this paper by Isett, which was the author of the last paper, of the Hilder with 1/5. He published this paper with this title, A Proof of Onsager's Conjecture. So indeed, it is a construction in the required regularity. So it's Hilbert with alpha less than 1/3, both in space and time. It works on the torus, and it has compact support in time. And this is the theorem. So for any alpha less than 1/3, there is a non-zero weak solution to the Euler equations in this regularity, such that U is identically zero outside a finite time interval. So it has compact support in time, but with the regularity required by Onsager. Okay, so there are some comments. The first is that the proof combines two ingredients. So it uses convex integration. And now, instead of Beltrami flows, it uses Mikado flows, which is a different stationary solution of the Euler equations, it was established in 2017 by Danelli and Sekelhidi. So he uses this as an ingredient for the convex integration, and it has some nice properties of how the frequencies interact, and this gives an advantage of technical advantages to make the regularity and the proof. But only those building blocks were not sufficient. So he has also a new technique, which is he calls gluing construction, because you are gluing some kind of parts of the solutions. And so he combines these two ingredients to perform a complete proof. And the solution has compact support in time, so it fails to conserve energy. However, it's not strictly dissipative, because it lies on that case of compact support solutions. And the proof is rather complicated. Actually, this paper has almost 100 pages long, and even people from the field publishing theorems about convex integration, they say that they still don't understand everything. So it's a very complicated proof, and people are still discussing some technical details. But it's a proof in this sense. The only thing that it lacks is the strictly dissipative part, right? And these are the Mikado flows. I'll just show, not the formulation, but show the picture. And this name comes from this game, which in Portuguese we say pega vareta, right? But it looks like I don't know if in Japan it's also called Mikado, and we can see that it resembles Mikados because the solution is composed by several vorticity tubes, which are essentially entangled, not entangled in the topological sense, but they are somehow constructed one above the other, and it's essentially a three-dimensional construction, right? And as I mentioned, the idea is that to construct a sequence of solutions and to perform perturbations with these Mikado flows. And at each step, you perform a different perturbation, which is it's operated at frequencies more and more frequent, right? More and more oscillatory. So we can see that this is the first generation. Then the second one, it's way more detailed, so it's in a finer scale, and then in an even finer scale, and so on. So this is these are the building blocks of the proof, and to use convex integration, the perturbation you perform in the solution, right? Okay. And finally, we have this paper from, this is from 2019. There is a typo here. By Bookmaster, Dalelis, Sekelhidi, and Vladvikol, which is a proof in the same regularity required by Onsager in the Hilbert 1/3. But now we are prescribing the energy evolution, just like the other theorems before, right? So assume we have an energy profile, a positive smooth function, then for any exponent less than 1/3, there exists a weak solution to the Euler equations in this class whose energy is E of t. And so we can perform, we can obtain solutions which are indeed dissipative, right? And apparently this finishes the whole problem, right? And it's very based on Mikado flows as well. So they are, again, the building blocks of this proof. Okay. So this is the review I wanted to show to you. And now I just want to give a glimpse, just the general idea of what is convex integration applied to hydrodynamics. And it's somehow very technical, but I want to give a glimpse in the sense that what is the idea beneath it, okay? So the first thing is that the ideas of convex integration, they come from John Nash in his celebrated theorems about embeddings for Riemannian manifolds. So in geometry, there are those questions about whether you can embed some manifold in an Euclidean space or in a higher dimensional manifold. And the idea of embedding is exactly that you are somehow putting the manifold in another space, but still preserving all properties, like topological properties or differentiable properties. And there was an open problem about isometric embeddings. So an embed which preserves metrics, preserves the Riemannian metrics. And John Nash was able to prove, I think that there are two theorems, and the question was exactly if we can obtain a C1 embedding of a manifold to an Euclidean space of some given dimension, preserving metric. And he was able to prove that. And after that, we have some other developments of this convex integration technique, like the Misha-Gromov. And the ideas applied in hydrodynamics are inspired by these results from John Nash and Gromov. And the idea is the following. We construct a sequence of approximated solutions, UK, satisfying the Euler equations, but they are approximated, so they are actually satisfying the Euler equations with an error, let's say an error, f of k. And the idea is to perturb these Euler equations with those errors, which we can interpret as forces. So these are the ghost forces from Schneermann. And the idea is to construct this sequence in such a way that these forces, they're becoming more and more oscillatory. So they are exciting the equation at higher and higher frequencies. And this, if we recall from harmonic analysis, if we are exciting higher and higher frequencies, we are converging to zero weakly in some weak topology, right? Just remember that there are several formulations of this theorem, but you can, if you integrate a smooth function against an exponent, an exponential, which is highly oscillatory, and if you send the frequency to infinity, you are integrating some smooth function against a sign, which is becoming more and more oscillatory, and this goes to zero. So there are some many formulations of this theorem from harmonic analysis, but this is the essence. And we can also see this in Fourier space. It's like you are acting on higher and higher k's. So it's all zero except for a high k, and this high k is moving towards infinity, right? So it's converging to zero in a weak sense. So this is the idea. We perform a sequence of solutions which are forced by something which is more and more oscillatory and which converges to zero. So this is the idea. You are putting forces into the system, but you know that those forces are going to vanish in the topology you are working with. So it's in a weak topology, it's going to zero. This resembles the idea from Alexei just presented before about noise. Because you need, if you want to study spontaneous stochastics, you need to somehow put stochasticity. So you put noise, but you get rid of that. You collapse noise. Here the same thing. If you want to create something out of nothing, we need forces, right? So we put forces, but we get rid of them. and we get rid of them in a mathematical way that we know we can do it. So this is the essence of idea. And now I will follow one of the constructions briefly, not the details, but just briefly to see how they do this, how to perturb the solution with those FKs. So this is the 2009 paper by Camilo Delelles and Sekilhidi. And the same construction is essentially the same construction as those another Hilder with 1/10, 1/5, right? Using Beltrami flows. So they work, the approximate solution will be, the approximate equation will be this one. So the Euler equations perturbed by this force, which is put in this form, the divergence of a tensor. And they put in this form because this tensor has a physical meaning. It's called Reynolds stress. So if we remember from basic turbulence course, if we take, for example, the average of the Navier-Stokes equations, the nonlinear term will produce an additional term, which is the Reynolds stress, the Reynolds stresses which are somehow stresses due to oscillations, turbulent oscillations, right? It's somehow connected with that. So they also give this mathematical form just to motivate physically. Okay, so they work with this perturbed equation, and they construct solutions, approximate solutions of this equation, converging in such a way that the idea is that the Reynolds stresses are going to vanish. Okay. So this is the proposition. So let E is the energy profile we are prescribing, right? So it affirms that, let's take a look. Take a delta, less or equal than 1, and suppose we have a triple, which is velocity, pressure, and Reynolds stress, okay? A smooth solution of the Euler-Reynolds system, which is that system perturbed by Reynolds stresses. Satisfying these conditions, so the energy of this flow, V, is close to the prescribed energy from below and from the upper and lower part by these constants and the profile multiplied by delta, right? So suppose it satisfies this, and also it satisfies the supremum of the Reynolds stress satisfies this bound by delta. So this proposition asserts that if we have such triple, then we construct a second triple, V1, P1, R1, which satisfies all the same things, but with delta over 2. You know, there is a lot of notation here, but this is essentially the same thing, you see? It's, here it's 3/4 of delta, here we have 3/8, right? And here we have 5/4, here we have 5/8. And here for the divergence, for the Reynolds stress, we have delta. Here we have delta over 2. So if we have this proposition proved, then we may construct our sequence of solutions, right? Because we start with the solution 0, identically 0, and then the identically 0 solution satisfies this trivially, and then we can obtain another triple which satisfies the same condition but with delta over 2, which is our first guy of the sequence, V1, P1, R1. Then we perform again with a different delta. And then we obtain a second triple with delta over 2, and then delta over 4, delta over 8, and so on. So we construct a sequence of solutions just using this inductive process. And we can see that the Reynolds stresses are going to vanish because delta is vanishing. And the energy of the flow is converging to the prescribed energy. Because delta is vanishing both from below and from the upper part. Okay. So if we have this proposition, we have the sequence, and we have, of course, there is a technical part, which is to prove that V lies on the regularity class we want. And this is PDE. So we construct by hand, and we perform estimates and prove that it lies on the spaces we want. But this is the convex integration step. Okay, so we need to prove this proposition. And how do, this is the difficult part, because it's constructed by hand. So how they do that? They consider V1 will be, so we have a triple V, P and R, and we are going to construct V. So V1, we are going to construct V1. So V1 is obtained from V by adding two parts. The first one is W0, which is the oscillatory part. It has very, very high frequencies. And as we go to infinity in our sequence, it becomes more and more oscillatory. So it's the oscillatory part. But this oscillatory part is not necessarily incompressible. So we just need to add a correction to transform the whole sum into incompressible. So this is the term WC, right? And then we use Beltrami flows, or in another case, Mikado flows and other flows, because we construct by hand. This is an explicit formula for W0. So I'll not put details here, but the things that there are several guys here appearing and constant, and you need to estimate all of them and to see that we need to control those constants and those functions to guarantee both convergence of the solution, the proof of proposition, and also that they lie on the desired spaces. And things here get technical. But the things that we can give explicitly our oscillatory part, and the terms appearing here, they come from Beltrami flows. So we know what are Beltrami flows, and we construct them in specific oscillations, and then we give our perturbation, the perturbation we have.
The terms come from these Beltrami flows are phi, r.
Yeah. I think phi. I think it's a kind of basis, and they come from K, and you can see that here we have also an oscillatory part, which is proportional to K, and this is the part you are going to send to infinity, no, because it's becoming more and more oscillatory. But there are also other functions like Rho, and there are specific things to guarantee the convergence you want, Okay, so this is all I wanted to talk today, is just to give a summary of the results and a glimpse of the technique. And I put this slide as discussion just to mention some things like what is the message of all of this, Because I think this is the object, the subject of the course. Like we have the equations, but what are the solutions, right? Are those weak solutions the solutions we want? Because are they physical? Do they have physical meaning? Are they representative? Are those constructions giving some insights to us about turbulence or the phenomena? And these are some questions that people are discussing now, because we can see that the results are pretty recent, right, 4 years ago. So people are still discussing those things. And I think that something we can state, which is very, very clear, and which is connected with everything Alexei and Simon were talking, is that weak solutions, in the sense we just discussed, they are non-unique. They are non-unique. This is proved. And people usually say that a message from these theorems is that apparently, because we don't have uniqueness, and they are somehow most of the solutions will have non-physical meaning. The message is that it looks like the space, let's say the space, the formulation of weak solutions is too large. It's too large. When we require smoothness, it's too strict, you see, because they are conservative. They cannot represent turbulent flows. They cannot dissipate energy, which is something we see from experiments in turbulence. So it's too strict. But if we relax to weak solutions, it's somehow too large, because there are several solutions which are not physically relevant. You know? So in some sense, maybe there is something in between. Maybe there is another formulation. And this is where spontaneous stochasticity comes. It comes from some ideas aiming to somehow give the right space, you know, the probability space for which is physically relevant, you know. But there are several questions, several things going on, and there's several open problems concerning these questions. But this is the idea, and maybe somehow the measure associated with the physical solution will be somehow a collection of weak solutions, or some of the weak solutions, which have no contribution per se. You know, they have no contribution. They have zero probability of occurring. You know, they have zero measure. So this is some possible interpretation, but of course, totally open, right? Okay, so I think I'll finish here, and thank you very much.